everybody, and welcome to today's assignment, assignment 4.1. Project is linked lists implemented as a stack and a queue. So for this assignment, I had to write a program that would use a stack and a queue as a doubly linked list. I had to have three functions in it: an insert, a remove, and a print for both the stack and the queue. It had to be done as one program. And we have to do a test for inserts and deletes at intervals of 100, 1000, and 10,000 random integers, both inserts and deletes. So, and the Excel spreadsheet will look something like this. So let's get into this here. I did that. So what I did is I took the code that we did in class, and I used that for the stack. That actually worked pretty good. And then, yeah, it worked really good actually. And then I built a queue. I had to do some research, and I found a place online that had a really nice example. I think it was Stack Overflow or something like that. But I kind of went through their code and then built my queue on that. So let's get into it, and I'll show you what's going on. So for the node, the class node, as you know, a node has a pointer and some form of data. So that pointer is going to either point to, if it's a singly linked list, then it's going to point next. If it's a doubly linked list, we need two of them, one to next, one to previous, so you can traverse forward and backwards. I had to put this static get node into this because it was using it for the queue. Although after I went through and wrote this program, I realized I could have did this a different way, and I really didn't need it. But I decided to do it this way. And basically, we're making a node called new node, and it's going to be the size of node, right? And then we're going to put in the data from the new node. The new node's data is going to equal data, and previous new node is going to equal to new node next equals null, return new node. So what that does is it basically says that if it's a previous and a next, if the previous equals next, if the new node previous is equal to the new node next, in other words, if they're the same, then it's going to equal null. Because think about it. If you're on the right-hand side of this list, and there's a left-hand side of the list, and you're going from the previous and the next, so in other words, you're either going forward or backward. If they are both the same, if the previous equals the next, then that means we have nothing left and it should equal null. Okay, understand this. Now, the class of stack, I have a node called head, and that's always going to point to the front of the node basically. And then I have an integer called length, and that's going to basically give me the length of what I need. So we have a constructor, stack, and then we have an insert, a display, and then we did the demo previous, and then the remove stack. So I kept these in here, but we're just using the display and the remove stack and the insert. For the class of queue, it's a little different. You have to have two nodes, one for the front and one for the rear. You can actually do this with a stack too, because you can actually insert from the front or you can insert from the rear, okay? But with both of these, with the stack and the queue, we're always inserting from the front. I just wanted to show you that you can do that, okay? You can also erase or remove from the front and remove from the rear. Doesn't matter if it's a stack or a queue. A node, a doubly linked list with nodes can do that. You can take something out of the front or out of the rear And if you really want to, you could probably do it in the middle, but it would have to involve some finagling. Okay, then we have an integer size, but I just wanted to let you know that I understand that. So in the Q we have a Q constructor, and the front, if the front is equal to rear, it's going to equal null and size of 0. So we kind of just basically zero that out, right? Okay, so I found all of these really cool functions that you can do, and this would work with just about any data structure, to be honest with you. Insert front, insert rear, delete front, delete rear, get the front number, get the rear number, get the size of it. Is it empty? Erase and display. We're only using a couple in here though, but I have them in here to show you, just to show you what you can do. However, only using insert front because this is a queue and we're inserting from the front, not the back, right? So it's first in, last out, right? So, you keep inserting in the front and that one gets pushed back, and then you take it off the back. That's how a queue works. While a stack, you push it in and push it in and push it in, and you just take it off the top. The last one you put in, the one that you put in previous is basically what I'm going to say is, well, how can I explain this? Because it's going to sound weird. All right, think of a stack of plates, right? You have one plate on top of another, okay? But instead of taking the very first plate you put in there for a stack, you're taking the last one that you put in off the top. While a queue, it's just the opposite. You're taking the one on the bottom, right? Okay, so that's how it works. Now, classes right here. So the stack, we have a head and it equals null, right? That is your constructor. Display, as you can know, we did this, or we did it all in class. So, but I'll go over it. So we have a node called current, and it's going to equal the head. And while current is there, the node, you're going to have a node equal the current data, and then you're going to go to the next current, right? So that's how it works. So the display is basically you're starting from the the top and working your way down to the bottom. All right. It's just displaying it in order. Now the insert, you have a node called new node, and it equals new node. And I actually did that in the beginning with node, if that's what we were pretty much doing. This new node is going to it's going to get into data, and the data is going to equal the number. So the number is basically what we're inserting in here. That's your arguments, basically. If the head is equal to null, then the new node is going to get the previous and equal that to null. And then it's also going to get the next, and the next is going to now become the head, and the head is now going to become new node, if that makes sense. Otherwise, new node's next is going to equal the head. The head is going to equal the previous, or the head's previous is going to equal new node, and the head is going to equal new node. Okay, demo we're not going to go into because that was it. Remove stack if the head is not equal to null. So in other words, if there's something in the head, you're going to get a node, a pointer called current, and it's going to equal to the head, right? Then we're going to output the head's data, and we're going to say it was removed in the stack, and then the head is going to equal the head pointing to the next. The head dot next, I want to say. So the member function next, or whatever, however you want to do it. So I had to take this head previous null out because it was giving me a null pointer at the end. We didn't need it actually, and I'll show you that. And it's true. You'll see it when it's working. Otherwise, empty list, you didn't remove anything. So here's some functions for the queue. So empty, it's just a boolean to see if it's empty or not. It returns front equals null if it's empty. Function to return, this is the elements in the queue, this is the size, this is what's at this is inserting an element at the front. So we're going to take data, a node, new node, get node data. So remember, that's what we were working on in the other node. the static get node. So if it's true, element can't be added and overflow is going to be printed out. Okay, so if new node equals null, then you have an overflow. Otherwise, if the front is equal to null, the rear is going to equal the front, and we're gonna make that a new node. So this is how we insert. Actually, this should be, that's not DQ. It should be, sorry about that. So if the queue is empty, that's what happens. Now, if we're going to insert the node at the front end, you do it basically like you did, with the stack. New node next equals the front, though, instead of the head, because instead of the head, we have a front and a rear. The front is going to equal the previous, and it's going to equal a new node, and front is going to equal a new node, right? So I want you to think about something here. You have a timeline. It goes from left to right. It reads from left to right. Left is 0. Okay, left is the start, right is the end. Okay, so when we're doing this, we're going backwards, right? When we're inserting this in the front. Okay. For this one, we're doing it just the opposite. The front is going to be the front of the queue, right? It's going to be the front. Then we're going backwards, previous. And that's how we're going to add things into this, right? I'll show you. Anyway, you'll see what I mean. Okay, and then we increment it by the size of 1. Now we have insert rear, and that does just the opposite. So, and it brings things to the rear. We have a delete from the front. We're not going to use this because we want this to act like a queue, and we're going to delete it from the rear. So here's your delete from the rear. Node, we have a temp, it equals rear. We're going to see out rear the data in rear, and then rear is going to equal rear previous. So we're stepping backwards, right? Okay. If there's one element only present, then the rear is equal to null. Front is going to, if the rear is equal to null, then the front's going to equal to null, and basically it's all null. Else the rear's next is null. So in other words, if you're at the rear and you jump to the next one, it should be null, right? Because we took it out. Okay. And then we free the temp. Okay. So we're not using the size. We're not using that. Get front, get rear. Yeah, so it's basically just a getter, If it's empty, you're going to return -1, return. If not, then rear is going to equal the data. And then we have an erase. And like I said, these are all things that we can implement, but I didn't implement them. I just wanted to show you guys that they were out there. Here's the display for the queue. So the node current is going to equal to the front. While current, you're going to output the data, and then you're going to go to next. Okay. All right. So here's how this works. Now, in the main program, we start a clock. Now, this screwed me up royally in the beginning, okay? So, I have a clock, a start clock and an end clock. We're calling a stack called my stack. So, we're making a linked list stack. Now, you have to put the start and the end outside of the for loop. If you put them inside of the for loop, it's going to be 0. Yeah. You want to make sure that you start before the for loop and you end right after it, so you're cycling all the way through it. Otherwise, you're not going to get the right answer. We're going to drop these down to 100 for now because I'm going to show you what's going on with this. Now, after we go through this iteration of 100 times, we're inserting random numbers into the stack. Then we're ending the clock. Then we're going to display what is in the stack, okay? And we're going to tell you the time it took. All right, that is how we populate the stack. Now, how we're going to remove it is we're going to do this. We're going to make another clock. You probably, I'm not sure if you can reuse the same clocks, but I find it just for myself, I like to keep things on different clocks. That way I have more control over it. So again, we start the clock outside of the for loop. And then we call remove stack from my stack. And that's going to go 100 times. So we're going to remove 100 things. And then we stop the clock, and then we display it. And then we display if there's anything left, and there's usually not. And then we print out the time. Okay? That ends the stack program. The queue program starts here. We have a queue, and I named it my queue. We have another clock. Okay, two of them start and end. We start the clock just like we do with the for loop, so we're going to iterate the for loop again. We're going to use the same type of for loop. Let me bring this down a little bit. And then we insert everything in the front, right? So it goes front to back. So we start at the front, all right, and we add one. And then we add another one. That previous one gets pushed to the back, and we put another one in front, okay? Kind of like a train, you know. It's going down the line. That's how it works. Then we end the clock, and we display it, and we say how much time it took by taking the end of the clock minus the start clock. And then to delete it, we do the same thing. A clock, a for loop, delete rear. So instead of the front, we're going to delete it from the rear. That's the difference between a stack and a queue. One deletes it from the front, the other one deletes it from the back. However, you can really do a lot of stuff with this because you can make functions that delete from the front and delete from the back. So really, you don't really need two different classes to say, like I did, right? It's one way of doing it. I did it one way. I made two different classes, and I used these things basically. You know, I just wanted to do basic stuff. But just to let you know, we can do it in one class, and we can delete from the front and delete from the rear, and it'll act just like a class or a stack or a queue. All right, and that's it. That's really all you need to do. And if I were to rewrite this, that's exactly how I would do it. You know, I didn't actually know that until I went through the code, and that's it. So anyway, that's it. That's how this works. So I'm going to demonstrate it for you, doing 100 and then 1,000, and I'll show you how that works. And then I'll show you the statistics. I'm not going to do the 10,000 because it's not going to show you everything. It only picks up at the end. And I figured this will be good enough. You know, you just want to see the program working. And then I'll give you the statistics that I got after that, and we'll go from there. Okay. So we're going to do 100. Alrighty. Let's start at the beginning. So we start by populating 100 places in this stack. Okay. It took 0 milliseconds. It was fast. Now we're removing it. Okay. We start 41, 29, 82, 18. It tripped me out for a minute because the last one was the same number as the first one, 41. So 49, 29, 82. Now if you look, we're going from top to bottom, not from bottom to top, because if we go from bottom to top, it would be 41, but it wouldn't be 67 or 34. It'd be 29 and 82. So we are doing this as a stack. Everything is coming off the top, not the bottom. Okay. Okay, so then after we do the bottom, or after we remove everything in the stack, it took us 38 milliseconds. Okay. Now we're going to populate a queue. And we start at 14, and we're going all the way down here to 33. All right. This did it pretty fast. So, but now we're going to take things from the bottom and work our way out. As you can see, 33, 33, 15, 15, 39, 39, 58, 58, 44, and vice versa, and so on, I should say. So as you can see, it is acting as a queue, and it is taking the last one out every time. And this one took 13 milliseconds. So now let's go ahead and try 1,000. We're going to go ahead here and 1,000, 1,000. And then for the Q, we're going to do the same thing. Okay, now let's run this. Okay, so let's go from the top. 2,000 starts at 249. All right. Oh my gosh, look at all of these. Look at them all. Come on. 1,000 of them. We'll get there sooner or later. Okay. All of that took only 1 millisecond, right? But now we're going to remove them. And as you remember, it started at 249 and now it's working its way from top to bottom, right? Just like a stack would work. Go all the way down here. Oh my goodness. Now you notice it says remove and stack, right? I wanted to determine a stack and a queue. All right, that took 152 milliseconds. Now we're going to do this for the queue. Notice it starts at 882, 279, 738. Okay. Let's go to the bottom. Bottom is 667, and then going up it's 528, 679. So it only took 1 millisecond to do all those. Now going and removing it in reverse, right? 667, 528 to 528, 679. So as you can see, again, we are removing from the bottom to the top. And it took 134 milliseconds. So that's pretty much it. That's how it works, guys. 10,000 is going to be a little much, and I don't want to bore you with that. But I will give you the statistics that I have. And that is, for the stack, an insert of 100 is 0 milliseconds. An insert of 1,000 is 1 millisecond. An insert of 10,000 is 2 milliseconds. A delete of 100 is 11 milliseconds. A delete of 1,000 is 153 milliseconds. And the delete of 10,000 is 1,374 milliseconds, or 1.374 seconds. Q, very similar here on the inserts. At the 100 and 1,000, they're at 0. Insert of 2, or at 10,000 is 2, just like the stack. The deletes, well, so it costs it a little more here at the 100 on the deletes than the stack, but it dropped for the deletes to 1,000 by a couple of milliseconds, and then maybe just a little bit more on the 10,000 milliseconds. So it's pretty consistent. It looks consistent to me on what the data is showing me so far, is that exponentially the delay goes up as more things are added to it. And it takes a lot more processing power to delete than it does to insert. So that's my presentation, guys. Hope you liked it. And if you like what you see, give me an A. You know I love A's. And I will talk to you guys later. Have a wonderful day.